Today we're going to talk about how to do sketches of graphs, in particular taking advantage of some of the things we've learned about the first derivative and the second derivative, and at the same time recapping some stuff that you may remember from algebra. So I'm going to talk about this just by diving straight into an example. So here's a function. So that's a fairly simple third-degree polynomial. We could whip out a graphing calculator or GeoGebra and take a look at what this looks like. But again, that only gives you a window on a partial view of the graph. It would be nice to have some confidence about everything that's possible in this graph. And so that's what we're going to try and do. So I've got this checklist of tactics I'm going to use for trying to come up with a sketch for this graph. And I'll keep my little checklist down here. So the first thing I'm going to think about is the domain of the function. Are there any x values that can't be input into this equation? This is a simple polynomial. It has no restrictions on its domain. We go from negative infinity to positive infinity. No big deal. Let's also talk about the zeros of this function, which is to say, where does it cross the x-axis? Where is y equal to 0? So if I set this whole thing equal to 0, let's see, I can factor an x out. And I can factor that binomial that remains, and let's see. And so using the zero product principle, I get x equals 0, x equals a positive 5, x equals negative 1. So those are the places where this graph is going to cross the x-axis. Okay, let's also talk about critical points. So critical points are those places where the first derivative of the function is either equal to 0 or does not exist. So let's start by taking the first derivative. Oh, sorry, made a mistake here. Okay, so there's my first derivative. Now, there are no x values I could plug in that makes this first derivative does not exist. So I can rule out that category of critical points right away. As far as finding the values that set this equal to 0, from eyeballing this, I don't see a way to factor this by hand. No, definitely, there's no way to factor this by hand. So we're going to fall back on our friend, the quadratic equation. I know you're excited about that. So when you've got an x squared, an x, and a constant equal to 0, the quadratic equation is, say it together with me, negative b plus or minus square root of b squared minus 4ac all over 2a. Whew. Okay, let's try that. So negative b, negative 8, so that gives me 8 plus or minus square root. Negative 8 squared is 64 minus 4 times a, which is 3, times c, which is minus 5. All over 2 times a. Oh, good grief. This is going to be 8 plus or minus 124 over 6. I can factor a 4 out. Well, I can factor a 4 out of the 124, which is a 2 when I bring it out of the radical. I could cancel everything by a 2, but really I just want approximate values at this point. So let's see, I've done the calculations ahead of time, and this is approximately equal to minus 0.52 and a positive 3.1893. Ugh. So my critical points. And let's take a look at what happens if I plot these on a number line. This is my first derivative. I've got two values, minus 0.5 and a positive 3.2. If I check my function, my first derivative, the sign of it on each side of these critical points, let's try a -1 plugged into my first derivative. That'll become a positive 3 plus 8 is 11, so I get a positive over here. Between these two, I'll pick 0. I get 0, 0, minus 5. That's a negative. And if I pick something like 4, I get 3 times 16 minus 32. That's going to be a positive. So now I know my sign changes. I know I've got positive slopes, a peak, negative slopes, peak, positive slopes. At least I think that's what it looks like. We're now going to double check this by looking at points of inflection, which is based on my second derivative. So we're going to do this same routine again, only this time with the second derivative. So f double prime of x, starting from right here. There are no x values I can plug in. That makes my second derivative does not exist. But if I set it equal to 0, I believe I get 4/3. And again, let's check this on the number line. 4/3. So this is my inflection point. If I take a value bigger than this, say 2, plug it into my equation, I'll get a positive on this side. If I pick a value lower than 4/3, like 0, I get a negative on this side. So that indicates that at 4/3, I've got something that's concave down, on past 4/3, concave up. And that sort of corresponds with our intuition from looking at the first derivative up above. So I think we've got everything we need to graph this function. Just to recap, the function goes all the way from negative infinity to positive infinity. It's got zeros at 0, -1, positive 5, so it crosses the x-axis in those places. It has critical points at approximately -1/2, so down here, and at positive 3, so right about here. We know its slope is positive leading up to this, so it crosses through the 0, positive, somewhere. I haven't bothered to figure out where. I could always take this -0.5, plug it into my original equation, and get a y value. I know it crosses back down here. All of this is concave down. I know that because of this. Somewhere around 4/3, let's say that's right there, I hit an inflection point and my concavity changes from concave down to concave up. Here's my other critical point, and then it passes through 5. This point is roughly 3.2. And that's our function. We know it doesn't have any other dips or local minimums, local maximums anywhere else, because we know our only critical points are right here and right here. So it goes forever to negative infinity from here, forever up to positive infinity from here.